Hyperbolic function. Hyperbolic functions are mathematical functions that are analogs of trigonometric functions, but for the hyperbola, defined using exponential functions. The basic hyperbolic functions are hyperbolic sine x, hyperbolic cos x, hyperbolic tan x, hyperbolic cotangent x, hyperbolic secant x, and hyperbolic cosine x. The h in the names of hyperbolic functions, such as hyperbolic sine x and hyperbolic cosine x, signifies their connection to the geometry of hyperbola, similar to how trigonometric functions are related to the unit circle, while trigonometric functions describe relationship in circular motion. Hyperbolic functions describe analogous relationship in hyperbolic geometry, which is based on the equation x squared minus y squared is equal to 1. The h helps differentiate this function from the trigonometric ones, indicating that they arise from exponential expression, connected to hyperbolic rather than circular motion. It is just related to trigonometric function, but it is related on the unit of circle. On the other hand, hyperbolic function is related on the hyperbola. So, why hyperbolic function is related to hyperbola? So, we have hyperbolic sine x is equal to e to the power of x minus e to the power of negative x all over 2. So, we're gonna break it into 2. So, we have hyperbolic sine x is equal to 1 half e to the power of x minus 1 half e to the power of negative x. So, what's that mean graphically? If we sketch this up, we get hyperbolic sine x. This one has a domain and range of all real number. Now, the hyperbolic cos x. Hyperbolic cos x is equal to e to the power of x plus e to the power of negative x all over 2. The same we do on the hyperbolic sine x, we're gonna break it. So we get hyperbolic cos x is equal to 1 half e to the power of x plus 1 half e to the power of negative x. We just need to change negative into positive. If we sketch this up, we get hyperbolic cos x. This one has a domain of all real numbers and a range of 1 to positive infinity. The hyperbolic tangent x will just be the hyperbolic sine x all over hyperbolic cos x, with horizontal asymptotes at y is equal to negative 1 and 1. The domain is all real numbers and range is negative 1 to 1. And then we have here the hyperbolic property of hyperbolic cosine, secant, and cotangent, which is just the reciprocal of hyperbolic sine, cos, and tan. These are the hyperbolic functions. It is just like a trigonometric functions. So it's very important to remember the trigonometric functions and identities. These are the identities of hyperbolic function. Familiar, right? Remember the trigonometric identities? From expression with squared function to these sum formulas. We just begin a simple equation. So example number 1 is hyperbolic sine 6x cubed. Then hyperbolic sine u times du. Our u is 6x cubed, and then the derivative of that is 18x squared. We're just using the power rule. Then distribute. The derivative of sine, hyperbolic sine is hyperbolic cos. The u is 6x cubed, and the derivative of u is 18x squared. And then we're gonna arrange it, and then we have 18x squared hyperbolic cos 6x cubed. So this is our first derivative. So our second example is hyperbolic tan x squared plus 1, and then hyperbolic tan u times du, and then our u is x squared plus 1, and then the derivative of that is 2x using the power rule, and then distribute. The derivative of hyperbolic tan is hyperbolic secant squared. Our u is x squared plus 1, and then our derivative u is 2x, and then arrange it. 2x secant hyperbolic secant squared x squared plus 1, and this is our first derivative. Our third example is y is equal to hyperbolic sine squared 5x. So first we're gonna be power ruling this one. So the power rule is 2 hyperbolic sine, and then 2 minus 1 5x, and then derivative of sine hyperbolic sine 5x. Y is equals to 2 hyperbolic sine, so 2 minus 1 is equals to 1, and then copy 5x, and the derivative of hyperbolic sine is hyperbolic cos, copy 5x, and then times derivative of 5x, and then copy 2 hyperbolic sine 5x, and then this one hyperbolic cos 5x, and the derivative of 5x is 5, and then 5 times 2 is equal to 10 hyperbolic sine 5x, copy, and this one's hyperbolic cos, copy. So this is our final answer. Our first example is y is equal to ln parenthesis hyperbolic tan 2x. So first we're gonna be deriving the ln, so the derivation of ln is 1 over u times du. Then 1 over, so our u is hyperbolic tan 2x, and then derivative of u, and then the derivative of 2x. So copy this one, so the derivative of hyperbolic tan 2x is hyperbolic secant squared 2x, and then the derivative of 2x is equals to 2, and then 1 times hyperbolic secant squared is hyperbolic secant squared 2x over hyperbolic tan 2x times 2. So 2 times hyperbolic secant squared 2x is equals to 2 hyperbolic secant squared 2x over hyperbolic tan 2x. So this is our answer. Our fifth example is y is equal to 4 hyperbolic cos 4x squared. And so let u is equal to 4x squared and our y is equal to 4 hyperbolic cos u. So we're going to use the chain rule for this. So dy over dx is equal to dy over du times du over dx is equal to d over du for hyperbolic cos 4x squared times d over dx for x squared. And then we're going to separate the 4 from the hyperbolic cos. So dy over dx is equal to 4 derivative of u. So cos hyperbolic cos u times derivative of 4x squared. So let us get the derivation of that. So 4 derivative of hyperbolic cos u is equal to hyperbolic sine u, and then the derivative of 4x squared is 8x, and then times the 4 and hyperbolic sine u and 8x, so 32x hyperbolic sine. So our u is 4x squared. So this is our answer. Our sixth example is y is equal to 2x minus 5 hyperbolic tan 3x plus 6. So we're going to use the product rule, which is v du plus u dv. Let u is equal to 2x minus 5 and our v is hyperbolic tan 3x plus 6. So the derivative of our u is 2 and the derivative of our tan is 3 hyperbolic second squared 3x plus 6. So and then substitute, which is our v is hyperbolic tan 3x plus 6 and our derivative of u is 2 plus u, which is 2x minus 5 and the derivative of v is 3 hyperbolic second squared 3x plus 6. And then simplify. 2 hyperbolic tan 3x plus 6 plus 3 2x minus 5 second hyperbolic second squared and then 3x plus 6. So this is our answer. So our seventh example is y is equal to hyperbolic secant e to the power of 2x, and then let u is equal to e to the power of 2x and y is equal to hyperbolic secant e. And we're going to use the chain rule, so dy over dx is equal to dy over du times du over dx is equal to derivative over dx is equal to negative 2e to the power of 2x hyperbolic secant e to the power of 2x hyperbolic tan e to the power of 2x. So this is our final answer. Our eighth example is y is equal to 11x minus 5 all over hyperbolic cotangent 2x. So we'll be using the quotient rule, which is v du minus u dv all over v squared. So dy over dx is equal to hyperbolic cotangent 2x derivative of 11x minus 5 minus 11x minus 5 derivative of hyperbolic cotangent 2x all over hyperbolic cotangent 2x squared, and then simplified. So dy over dx is equal to hyperbolic cotangent 2x. So derivative of 11x minus 5 is 11 minus 11x minus 5. Derivative of hyperbolic cotangent 2x, we'll be using chain rule for that. So d over du hyperbolic cotangent u derivative of 2x. So all over hyperbolic cotangent 2x, hyperbolic cotangent squared times 2x, and then dy over dx is equal to 11 hyperbolic cotangent 2x minus 11x minus 5. So derivative of hyperbolic cotangent u is negative cosine hyperbolic cosine squared u times 2 all over hyperbolic cotangent squared 2x. And then dy over dx is equal to 11 hyperbolic cotangent 2x plus 2 11x minus 5, and then hyperbolic cosine squared 2x all over hyperbolic cotangent squared 2x. So this is our final answer.